modules and detecting these subalgebras. Welcome, Matthew.
All right. Yes, thank you for introducing me. And I'd also like to thank the organizers for putting this on. So the first thing I have here is just kind of a list of the references. And kind of in particular, I want to point out two that really inspired the work that I'm going to speak on. So the first one is actually the first one here by Benson, Iyengar, and Krause on representations of finite groups, local cohomology, and support. And then the second one that I want to highlight is the one by Bo, Kujawa, and Nakano called Tensor Triangular Geometry for Classical Superalgebras. So the first thing I kind of want to tell you is, well, what is a tensor triangulated category? So a tensor triangulated category, or a TTC, well, first of all, it's a triangulated category. So you have these distinguished triangles, your category is additive, you have a shift, all subjected to sort of a list of axioms. And then, in addition to this, you have a monoidal structure, okay, so a tensor product with a unit. And okay, so I want to kind of insist that these functors are actually exact, these tensor functors. And also, I want to assume furthermore that my category is symmetric, monoidal. So the situation, the sort of non-commutative case, well, it has kind of been studied recently, but I'm not going to touch that today. Okay. So when you have a TTC, you can kind of think of it like a ring, because you have the addition with the direct sum, and then you have the product with the tensor product. And so we can kind of define some notions kind of analogous to what you do in commutative algebra. So maybe actually the first one kind of isn't really from commutative algebra, but I want to say that a localizing subcategory of a TTC is a triangulated subcategory that is sort of closed under set indexed coproducts. And then, okay, so this one kind of is more natural. A thick tensor ideal in K is going to be a thick triangulated subcategory I that sort of has this absorption property. So if you have M and I and N and K, then the tensor product should land in I again. Okay, so sort of a natural thing that we'd like to do given a TTC is to classify the localizing subcategories and these thick tensor ideals, okay? And yeah, I mean, in general, this is like a pretty difficult problem, but there are some cases where we kind of do have an answer. And one approach that you can take is to take advantage of the action of a graded commutative ring on your category, if you have such an action, okay? So actually, this is what I want to talk about next. So if you have a TTC, we define the graded center as being, well, it's a graded commutative ring, and in degree n consists of natural transformations from the identity to the shift, subject to this condition about commutativity up to sign with the shift, okay? And well, if you have a graded commutative ring R, then an action of R on K is a homomorphism from R to the graded center. Okay, so a homomorphism of graded rings. And if your category K actually admits such an action, then we call K an R-linear triangulated category. All right, so stratification. So what is this? So if you have an R-linear TTC, so an action of R, well, then you can look at the spectrum of R, and this is like the set where elements are the prime ideals. And for each P in the spectrum, you actually have this, what's called a local cohomology functor, okay? So the construction of these is quite technical, and I don't really want to get into it, but for our purposes, I want to think of these as being functors that kind of help us define a notion of support for objects in our category. So I want to say that the R support of an element, or an object rather, X, is going to be those prime ideals in the spectrum that sort of aren't killed by the local cohomology functor. And then, okay, I want to say that the R support of K, the category, is going to be those P's such that, well, the whole category is not killed, okay? And we say that a triangulated category K is stratified actually by the R action if the support kind of satisfies two conditions. So the first one is this local global principle, which says that for each object X, the localizing subcategory generated by X actually coincides with the localizing subcategory generated by gamma P X as P ranges over the spectrum. And then the second condition for stratification is this condition called the minimality condition, which says that for all P in the R support of K, the subcategory gamma P of K is actually a minimal localizing subcategory. And I guess I should point out here that if you want to show that a category is stratified, actually the first part, part A, the local global principle, isn't really what will hold you up. As far as I know, actually, there are no examples known where condition A fails. Condition B is more subtle and more difficult. All right. But okay, why did we define this notion in the first place? So, consequences. So if you actually have a R linear TTC stratified by the R action, then you actually have these bijections here. So the first one is a bijection actually between the localizing subcategories of K. So that initial problem that we wanted to address, and subsets of the R support. Okay, and these bijections are given pretty explicitly, although I didn't include them here. And well, the second one is that you actually kind of get this bijection between the thick subcategories, or if you have a TTC, the thick tensor ideals, and the specialization closed sets of specialization closed subsets of the R support. All right. Okay, so now I'm going to shift gears. So this is like a Lie theory conference. So why am I talking about this stuff? So Lie superalgebras are like the Z2 graded analog of ordinary Lie algebras. So, okay, I mean, it's a non-associative Z2 graded algebra, and the bracket, or the super bracket, satisfies the graded condition, the graded analogs of the ordinary Lie algebra axioms. So we have the super skew symmetry. So bracket of x and y is equal to the bracket of y in x up to a sign, depending on the grading of x and y. By the way, so these axioms are stated for elements which are pure in the grading, right? So you can kind of extend linearly. And then there's the graded analog of the Jacobi identity, the super Jacobi identity. So given a Lie superalgebra, okay, so the first thing that you can notice is actually this even part, G0, if you restrict the bracket, is actually going to be a Lie algebra in the ordinary sense, okay? And, well, we want to call a finite dimensional Lie superalgebra classical if there's a connected reductive algebraic group, big G0, such that Lie of G0 is the Lie algebra, okay? And the, you know, if you have ever seen this, then this is the example you saw. So the first example of a Lie superalgebra is this GLMN. So it consists of m plus n by m plus n matrices that kind of have this block form, and the bracket is sort of defined in this way. And so the even part is actually going to be these blocks on the main diagonal, and the odd part is the auxiliary diagonal. Okay. So if you have a classical Lie superalgebra, both Kujawa and Nakano actually proved the existence of what they call detecting subalgebras. And these are subalgebras which detect the cohomology. So specifically, if you have a classical Lie superalgebra, which admits something called a stable action of the algebraic group, then you can construct this subalgebra that I call F here. Actually, this is their notation. And then you have an isomorphism between the relative G0 cohomology and the relative F0 cohomology up to the n, which is a subgroup, the normalizer of G0 and H. Right? Okay. So if you have a Lie superalgebra, you can define the notion of a representation. And essentially what you do is you form the universal enveloping superalgebra as a quotient of the tensor algebra. This is quite familiar. And then a G supermodule is going to be a left UG module that's Z2 graded and respects the grading when you act by elements in G. Okay. Okay. Now I want to define the stable categories. So we call this CGG0 the category of G modules or supermodules, which are actually semi-simple over G0. And then FGG0 is going to be the full subcategory of CGG0, where the objects are the finite dimensional modules. Okay. And both of these categories have enough projectives, and they're Frobenius, and so we can form the stable module categories, stab FGG0 and stab CGG0. And these are actually TTCs, okay? So you can ask questions about the geometry, okay? And I want to kind of remark here that CGG0 is what's called a compactly generated TTC. And the compact objects are actually the objects of FGG0. Okay, so now that I've told you what a Lie superalgebra is and what the representations are, I want to kind of restrict to a special class of Lie superalgebras. And these are Lie superalgebras that I call type Z. Okay, and well, what they are they're Lie superalgebras where the even part is a torus, and when you bracket the even and the odd parts, you get 0. Okay, so it turns out that any Lie superalgebra satisfying this is going to be a classical Lie superalgebra, and any of the detecting subalgebras constructed by BKN would satisfy this condition. Okay, so I will, from now on, kind of let K be the big stable category of all Z0 representations, and KC for compact being the stable category of the F. Okay, and then BKN actually have this theorem where they compute the cohomology, the relative cohomology for Z. Okay, so there's actually an isomorphism between this relative cohomology in the symmetric algebra on Z1 star, okay? And moreover, they show that the thick tensor ideals in state FGG0 are in bijective correspondence with the specialization closed subsets of proj of the cohomology ring, okay? So what I want to talk about is actually how you could recover this. So in their paper, both Kujawa and Nakano conjectured that the category K is actually stratified by the action of the cohomology ring. And well, from an earlier slide, with a little bit more detail that maybe I didn't say, this would recover the theorem from the last slide as sort of an immediate consequence. But they didn't pursue this approach. And they use some, I say, heavy representation theoretic machinery. So our contribution is to actually, well, we wanted to actually pursue the stratification avenue. And we have the following theorem actually, that the TTC on stab CZZ0 is stratified by the action of the cohomology ring. And as an immediate corollary, the big tensor ideals in the stable module category of the smaller category, the compact part, are in bijective correspondence with the R supportive K, which turns out to be the proj of the symmetric algebra on Z1 star. Okay. So maybe let me say a little bit about how you're able to show something like this. So the idea, well, what we observed actually is that, yeah.
This last one, the G and the Z are.
The
I forgot how those are connected.
okay, so this should be a Z. Yes.
Ah, okay.
Yeah, yes. Okay, it should be state FZZ0. Thank you. Okay, so the way we were kind of able to do this is we observed that this is very similar to a situation that kind of has been considered. So if you have an elementary abelian 2 group, G, and you consider the group algebra over a field of characteristic 2, then this category state KG is stratified by the action of the cohomology ring. And well, because the situations are so similar, you can kind of use a similar argument to what they did to actually get our case, okay? And well, sort of the first thing to do, or the first thing to realize, is that if you have A being a commutative Noetherian ring, and you consider its derived category of A modules, then this derived category is actually stratified by the canonical action of A. Okay, so what the idea is actually is to kind of find a way to pass from this derived category over the cohomology ring to the stable category, okay? And you can't do it immediately, so you kind of need this intermediate category to do it. And this, what turns out to be the right thing to consider is actually the homotopy category of injective modules in CZZ0, okay, which I kind of denote here by K-inj, CZZ0. And what you can do is actually show sort of directly that K-inj is stratified by the action of the cohomology ring. And actually there is an equivalence of triangulated categories between this K-inj and the derived category. Okay, so then we kind of need, well, we need to get the stable category in the picture. And what you can show is that there's an equivalence of categories between the stable category and the homotopy category of injectives in CZZ0, but you consider only those acyclic complexes. And from here, actually, to complete the argument, you just kind of need to show that the R actions actually coincide, which is sort of an exercise in change of categories, like change of rings. All right. So I think I'll stop here. So thank you.